Good morning, everybody. We're back to our second day of the workshop with running CT, as they would say in Germany. I'm happy to hand the mic off now to Tess Smidt, who's going to be talking to us about the Euclidean neural networks. Thanks, Tess.
Thanks, Rafa. And thank you to the organizers for having me here. So far, it's been super fun, and I've been really enjoying everyone's talks and just getting to meet people. So I kind of work in this equivariant neural networks business. And so I thought I'd try and make a presentation that had a little bit of something for everyone. So I'll kind of give maybe some intuition and a bit of an overview on kind of how these networks work, cover a little bit of applications, and then kind of the last 5 minutes I'm going to spend on something a bit technical that I think at a high level, I think everyone should be able to follow. But I think even for folks who are kind of in the nitty-gritty method development of these networks, hopefully it's something a bit fun for you too. So the work that I'm going to show today, I'm going to hop around a little bit, but especially the ending part is kind of based on a lot of these two papers that I did with Mario Geiger and Ben Miller. And so, yeah, a lot of this work was done while I was still at Berkeley Lab. I just started at MIT. And so I just want to acknowledge Berkeley Lab and my funding sources while I was there. Geek. There we go. Okay. So two things maybe to keep in mind for this presentation, two questions that I'm really interested in my research is how do we kind of pick minimal yet really fundamental assumptions to build into neural networks? How do we go about doing that? And then what are the consequences of that? Because sometimes when you encode an assumption, it's not obvious to see all of the consequences that arise from those assumptions. So hopefully today I'll show you kind of some of the examples of how that arises. So I think several people have argued already, so I won't labor the point too much, but basically, geometry and symmetry are pretty fundamental assumptions to bake into machine learning models, and it's really helpful when you're basically building neural networks or kernel methods that, if you're on a geometric domain, that you include some information on that. And there's many ways to motivate this, but one that I always like is that coordinate systems are fundamentally arbitrary. In order to kind of write down things that exist in 3D space into something that a computer can understand, I have to lay down a coordinate system and write down my coordinates in that coordinate system. But really, the coordinate system's not really there. There's not a bunch of little rogue coordinate systems running around in the world. We always have the option to change our coordinate system. And in the case of 3D space, we can always transform our coordinate system via the symmetries of Euclidean space. So translation, rotation, and inversion. So making that a little bit more concrete, suppose I have a set of molecules and I choose coordinate system 1 versus coordinate system 2 to describe their coordinates in 3D space. The problem with giving these coordinates directly to traditional machine learning is that it'll see situation 1 and 2 as completely different and unrelated, when really they're just different ways of describing the same thing. And this is problematic because if your machine learning model is not built to handle symmetry, you have to resort to data augmentation. 2D, this isn't too bad, but in 3D, especially depending on the angular resolution that you need for your data, it can be as much as a 500-fold augmentation. And that doesn't just mean more training time, it also means more parameters in your model. It also means that you're never actually guaranteed that you're going to get the same answer if I or the same appropriate answer when I rotate my coordinate system. So this is just to kind of give you a sense, if I wanted to be able to identify this cube with colored edges, I'd have to show in a lot more examples than if I just trained with symmetry. Okay, so how do we go about this? Now, for making symmetry-aware models, there's generally two approaches, although it's not as clean-cut as maybe we'd all like, but basically there's invariant models, which are like, coordinate systems are annoying, why don't we just get rid of them? And instead of dealing with coordinates, why don't we deal with things that are invariant under a change of coordinates? So things like bond distances or distances between objects, angles, dihedrals, things like this. These are invariant quantities. So why don't we get rid of the coordinate system? Another approach is to say, okay, we're going to keep the coordinate system around and we're only going to apply operations that preserve the fact that this is an arbitrary choice. So basically treating the coordinate system fully, and these are equivariant models. And the nice thing is that they can operate directly on data that's based on a coordinate system, and all of your information will transform appropriately when you change your coordinate system. Okay, so what makes things a little bit more complicated? Oh, let me mute myself actually. Oh, I don't know how to do that without. Okay, there. I don't need to hear myself from my own laptop. Okay, so the problem that I think people run into is that, in fact, equivariant models are a bit more complicated to implement than invariant models. And I want to show you kind of just these toy interaction examples. So there's a notion of like features being invariant and equivariant. So like a scalar quantity like an energy is invariant, but something like a 3D vector is equivariant. But there's also a notion of kind of different orders of interactions. So how do I interact two scalar numbers? Well, it's pretty easy. A number times a number is a number. So that multiplication is pretty straightforward. And even in the case of where, let's say I have a 3D vector and a number, well, all a scalar can do to a vector is scale the vector. That's a scalar. And so these are sort of invariant interactions. These are scalar operations. There are actually several equivariant methods that only have scalar interactions. However, there's kind of a more and more general way to do multiplication and equivariant interactions. One example is, how do I multiply two vectors? Well, it's not really just one answer. Do you want the dot product, which would give me a scalar? Do I want the cross product, which would give me actually a pseudo vector? Or do I want like an outer product? Well, really, if you do the outer product, you actually secretly contain the dot product and the cross product. So outer products are actually sort of the most general in this space. And you could imagine that, let's say I start multiplying matrices by matrices and get more and more complicated. And there's a lot of mathematical machinery for kind of simplifying this so that you're not just getting a bunch of indices in your composable function. But this kind of gives you a sense of why it might be a little trickier to do equivariant interactions in a neural network. Okay, so one of the things I work on is Euclidean neural networks. So these are neural networks built specifically to handle 3D symmetry of Euclidean space, so translations, rotations, and inversion. And again, these networks understand that a physical system described by different coordinate systems still means the same thing, even without training. One reason why this is nice is I'm showing here a water molecule with different rotations, and then I'm showing you a Hamiltonian matrix, maybe calculated with density functional theory, showing this basically the interactions between the electrons on different orbitals of this water molecule. And basically, you know, the rotation here is matching the rotation here. This looks like a fairly simple rotation. It's just a rotation of a water molecule. But as you can see, this complex tensor object where the rows and columns are basically atom-centered basis functions, these are pretty complicated transformations. And this is something as simple as a humble water molecule. So it's really nice to build a model where you only have to show it one example and it's guaranteed to give you the right output. So hopefully that convinces you that this might be useful for physical properties. At a very, very high level, Euclidean neural networks are the mergers of the flexibility of neural networks with the rigors of representation theory. And just a very quick slide on that. So any machine learned model can be kind of abstracted as some function f that takes an input x, weights w, and produces some output y. And we typically have some way of evaluating the fitness of a given model, saying, okay, here's what I got, here's what I wanted. You know, if you're doing MSE loss, take the difference and square it. And that's how I'm saying, okay, how good is this model? And then neural networks have this specific criterion that the model has to be differentiable because of the manner in which we update our weights, which we take gradients of the loss with respect to every parameter of the model. And then we take a step of eta, that's our learning rate. And then we kind of continue on with our next iteration. So that's neural networks in one slide. Okay, what about group representation theory? I think for those with a materials or a chemistry background, this is the same branch of mathematics that brings you point groups, space groups, selection rules, and spectroscopy, and symmetry allowed and forbidden properties. So it's actually something that's really near and dear to the hearts of these fields. And the condition that you need to satisfy is actually not just F, the model, but actually every single operation of the model has to be constructed to follow this certain constraint. Basically, if I rotate the inputs, I could rotate the inputs or I could rotate the outputs, and I must be guaranteed to have the same answer. So this doesn't tell you how to build these functions. This tells you the condition that must be satisfied. And the key thing here that I want to emphasize is that what a rotation looks like on your input versus your output doesn't necessarily need to look the same. So let's say X is a 3D vector, that'd be a 3x3 rotation matrix, but my output could be a scalar, and that rotation actually just looks like the identity. Or if it was a 3x3 matrix, you'd need to contract a rotation on both indices. And then again, just to make it a little bit more concrete, what do you actually input into these models? Well, basically you have geometry, features on that geometry, and then one more other technical detail. You need to actually tell it, how did these features change under rotation, translation, inversion? So if I have these 2-point masses, they have 2 scalar masses. So they have like M0, M1. They have velocity and acceleration vectors. So those have each 3 numbers. I have where they are in 3D space. And then I additionally need to say, okay, the mass is a scalar quantity. It has 0 angular frequency, meaning it doesn't change under rotation. And also, if I invert my coordinate system from a right-handed to a left-handed coordinate system, it doesn't change. And these velocities and accelerations are vectors where they rotate with a change of the coordinate system with the same frequency. And they are odd under parity, meaning that they do incur a minus sign if I go from right-handed to left-handed. Okay, so that's a very, very quick introduction into these models. So we've been using these models to build very data efficient and scalable models of physical processes. And a really important part of this was actually building a general framework for articulating these interactions in an efficient manner so we could quickly prototype and try out new ideas. And so kind of my partner in crime on this, and now the benevolent dictator of this library of our E3 and N libraries, Mario Geiger. So we worked very hard on this library to deliver the most general mathematical operations that you could need to construct equivariant functions, regardless of whether you're doing neural networks or not. It's actually quite useful just for general tensor contractions. So if this is of all interest to you, this is a great resource for tutorials and resources on representation theory. Okay, so I'm just gonna kind of do a couple examples because of time. But currently, I hesitate to put up this exact slide because it's, is a molecular dynamics community. So I will just say that currently, Euclidean neural networks are certainly top competitors, if not state of the art, in several different types of molecular dynamics tasks. And so just to give some context, people have already talked about DeepMD, this model that won the Gordon Bell Prize for scaling ab initio molecular dynamics to 100 million atoms. Super cool effort, and not only a scientific feat, but also a feat of great engineering because they scaled it to Smidt, which has 27,000 GPUs. And if you're wondering what 100 million atoms looks like, it looks like that. And then, so with collaborators in Boris Kaczynski's group, and especially Simon Batzner and Albi Muzalian, so in January 2021, we sort of put out this first equivariant interatomic potential called NEQUIP, which folks have been citing in other talks. And what we found is that it was roughly 1,000 times more data efficient than DeepMD. So specifically, we looked at the water data set, and whereas DeepMD was trained on 100,000 examples, we were trained on 100, and we got better accuracy. So this was sort of a hint that, okay, maybe these equivariant models really have a place in this space of interatomic potentials. And then more recently, Allegra has come out showing that if we basically don't use a message passing graph neural network and instead have a fixed radius, we can actually still achieve like really good accuracy, basically competitive with NEQUIP. And using that type of strategy, they've been able to show that on about 100 GPUs, we can still, I think, punch out about I'm actually now forgetting the units. Is it a picosecond is kind of the metric that folks like to use in MD, or it's like, you were saying it was 13, you were simulating 13 yesterday. Which units was that? Okay, yeah, so I think it's 1 nanosecond per day on 100 GPUs. And all these codes are open source. So if you're interested in them, definitely check them out on GitHub, and there's some really good tutorials and documentation. Okay, I also want to emphasize this data efficiency is this is a work from the Drawer Lab, and the data efficiency of these models is actually enabling kind of crazy things where they're like predicting the accuracy of certain RNA structure predictions after training on only 18 examples from 2007. I thought this was super cool. They have a really nice science paper, so if this is of interest to you, I recommend you check it out. And they're using E3 and N as kind of the base for their code base, so it's really cool to see other people using the code. One other thing is, yeah, so equivariant models are more data efficient than even their invariant counterpoints, even when training on just invariant outputs. And what we're basically seeing is if you plot the loss on a log plot and you plot the number of examples on a log plot, you sort of get this like power law scaling. And essentially the slope is steeper for equivariant models, meaning you give it one example and it's going to learn faster than an invariant model. And I think Gabor might talk a little bit more about this. It's not quite as simple as just invariant equivariant. There's also notions of n-body scaling. But what's cool is that we're seeing this across different tasks and different works. People are observing this sort of change in the slope of how quickly these models learn compared to invariant versus equivariant counterparts. Okay, so I think I have a few more minutes. One thing I want to emphasize more of these consequences is that these models kind of had unexpected properties that are actually very similar to physical systems. And one of them is that the symmetry of the outputs have to have equal symmetry to the inputs. And this is a consequence that I'm showing here. Basically, if you take randomly initialized Euclidean neural networks and you have them output things that basically transform as spherical harmonics. So what I'm showing here are kind of things like SPD orbitals, just plotted in a specific way. If you take 3 randomly initialized models and I give them like a tetrahedron versus an octahedron, you can see that the outputs of these random untrained models have the same symmetry. These ones on top have at least tetrahedral symmetry, and the ones on the bottom have octahedral symmetry. And so that just gives you a sense that this is a pretty strong prior. It's really carving out your space of functions. And this also means like, if you care about space groups and point groups, you don't need to implement them individually. You implement Euclidean symmetry and you get any subgroup for free. And this symmetry preserving nature has consequences on training. So here's 2 simple tasks. I'm going to take the vertices of this rectangle and I'm going to predict vectors to deform it into this square. And then I'm going to do the opposite task. Now in the next slide, instead of showing you vectors, what I'm actually going to show you are distributions of vectors, which you can represent again as spherical harmonics. So don't be surprised if you see blobs on the next slide. But essentially, these models act as symmetry compilers. The first task is well defined. There's a unique solution that you can train to learn. Basically, you see this blob is kind of overlapping. The reason why it's not a delta function is I'm cutting off at a specific L. So in the limit of L goes to infinity for number of spherical harmonics, it'd be a delta function. But you get the idea if I only go up to L equals 5. But in the second situation, what's weird is it'll never train to learn this task. And the reason why is because the model basically predicts that there are degenerate outcomes, even though you showed it one example, which is pretty cool. It's basically the network saying that wasn't a well-defined question. Okay, so how do we fix this? How do we resolve degeneracy and symmetry preserving networks? Does this mean that we just have to deal with it, or is there something we can do? And there are actually ways you can do principled symmetry breaking. You can either break the symmetry of your inputs, or you can break the symmetry of the outputs via sampling. So the first case we talk about in this physical review research paper. And basically one way that you can do this is the gradients are also equivariant. So if your loss is showing a symmetry breaking, you can actually propagate that symmetry breaking to the inputs of your model. So you can almost learn these little order parameters that are symmetry breaking. And you can basically, instead of updating your weights that are scalars, you can update some sort of secondary input that's non-scalar. And you can basically learn what information was missing. What information did it need in order to accomplish this task? And in this case, it needed to be able to differentiate the X direction versus the Y direction, which you can do with specific spherical harmonics or different irreducible representations, some of which the spherical harmonics transform as. So what's cool about this is it'll only break the symmetries it needs to. And so this is a very rigorous way of understanding what's going on in your model or what missing data you might have. Okay. This is more recent thoughts. This is like stuff that I've been thinking about while zooming around to different workshops. You can also break the symmetry of the outputs. And one way to think about this is the predictions that the model is giving right now are X with 2 indices. It's basically the A index is which signal is on which atom, and then I is representing the actual coefficients of the spherical harmonic. And so what we have here is we have 2 states. 1 and 2, and we train on 1, and what we get is basically the superposition of state 1 and state 2. You can actually generalize this to higher order moments. So basically moments of both the permutation index, A and B, and the representation index, I and J, and you can construct these higher order matrices that look very similar, kind of analogous to the Hamiltonian matrix I showed earlier. And what's really cool is that you will also get this degeneracy in these moment tensors. So you basically train on this. You only need to know of one example and it'll automatically learn the ensemble. So to wrap up, why should we care that a symmetry-preserving network is really good at learning about degeneracy? Well, degeneracy implies that these models should be extremely efficient at learning ensembles, which my understanding should be pretty relevant to molecular dynamics. Basically, instead of doing molecular dynamics trajectories, like just one trajectory at a time, instead of one path, why don't we just evolve the whole distribution? This may be something that can be faithfully represented with these types of models. Other things for generative models, we often think about, an example encoding to one latent vector, but maybe there's sort of like a degenerate path of ways to encode an object. Maybe that's a good thing because we'll be able to more flexibly compare different similarity metrics. Maybe to make that a little bit more concrete, let's say I have a zinc blend structure. So this is a crystal structure with 2 distinct atoms. In this case, one of them is zinc and one of them is sulfur. And let's say I wanted to kind of pool these atoms into fewer and fewer atoms. There's sort of 2 ways to view this structure. Either it's like a face-centered cubic lattice of zinc that is tetrahedrally coordinated by sulfur, or I can actually think the reverse. Neither one is necessarily more correct. Maybe we want to encode both. Maybe there's structures where it's more helpful to think about it one way versus the other when we're making comparisons. So I think this issue of degeneracy could be quite interesting. So I think I'm a little over time. So I'm just going to leave these takeaways up here and I'm happy to take any questions you have. Thanks.
Thanks very much, Tess. Amazing talk and figures as always. Do we have any questions from the audience on the topic of equivariance? Okay, we've got one. I'm not going to run as fast as John.
Hi, thank you very much for your very nice talk. I have a kind of general question. When we think about these spherical harmonics, are we using this because there is some physical inductive bias in using them, or do you think there is some kind of mathematical reason they are better basis function or the only basis function that we should care about?
Yeah, so it's a great question. Like, why do spherical harmonics show up in this? Like, is it because we're doing chemistry or is it something more general? So it's something more general. Essentially, so if you're familiar with Fourier transforms, so I can basically do a Fourier transform over space. Spherical harmonics are the Fourier transform over angles. And so they're just a very useful set of orthogonal basis functions, and they have all these really nice transformation properties under rotation. So it's a much more fundamental thing. Nothing in here has anything to do with physics except for the fact that it's specifically 3-dimensional Euclidean space, which is the space we approximately live in as long as we're not going too fast or have black holes near our vicinity.
Thank you.
No.
Sorry, for a math question again. Are spherical harmonics then the only functions with these properties, or are there alternatives?
No, not at all. They're actually, what they are is, actually I was talking with Jonathan about this yesterday. So they're a set of functions that you can represent in Cartesian coordinates with a single coordinate that they're basically the simplest functions that transform as higher order spherical harmonics. So you could imagine making polynomials of X, Y, and Z that are maybe of order like 5, but they only transform like something like L equals 3. It's just that the spherical harmonics are a very special set of functions that it's kind of the simplest way to get to higher order features. And again, these are basis functions of the irreducible representations. They are not these irreducible representations, these mathematical objects that are sort of the fundamental data types of 3D space. But they have a lot of very nice properties, especially for representing distributions of vectors and just, yeah, as a basis for anything on the sphere.
So is there another basis set? I mean, let's
There are
Polynomials
degenerate.
out of it, but is there another genuine?
You're saying specifically for rotation? There are degenerate ways to define the spherical harmonics. There's different conventions. We've chosen a very specific convention for the spherical harmonics. So there's a lot of like gauge setting there. I'm sure there's lots of functions that have nice properties, but the spherical harmonics, I think, are the simplest.
Thank you.
Thank you for the talk. Sometimes I feel when I read the equivariant papers, I come away with the impression that everything is solved. Like, okay, well, I should just use any chip and you know, I've done everything. I was just wondering what you felt like, where are the areas we need to work to improve these models? They seem very powerful, very expressive. And yeah, I sometimes don't get that sense about what's next. Maybe.
Yeah, no, thanks for the question. There's a lot of work to do. I mean, there's a lot of engineering stuff too. And there's also a lot of, I think, like being cheeky about math. This really just lays out what are the operations you have to use or what are the rules you have to abide by. But there's still so much creativity and flexibility to be had in inventing new equivariant operations. For example, we have this one nonlinearity that we came up with, but like, or actually, I'm sorry, we re-implemented in E3N, but it was originally from spherical CNNs. There's a nice mappings there, but we'd never used it for anything. And it turns out that the Facebook catalysis team just used it in one of their models, and it worked really well for them. So that was kind of exciting. So there's still so much exploration to see like what equivariant operations are actually powerful and useful. Like we know the rules for how to kind of contract things down to single irrep indices and different rules, but I think there's still a lot of algorithmic fun to be had. So playing with these operations, and I find that using something like E3N is very helpful for playing with things and visualizing it.
So when we were trying to optimize TouchMD, which is TouchMD net, like the equivariant transformer. Initially, actually, we had an invariant transformer, and it was actually performing better on QM9 for predicting the U0, not the basic unit. And then there is this question of like, if we predict the energies, okay, you can have the equivariant weights, you can have lots of other things, but where does this is not even that much more expensive to a certain degree, no? To do the
depends on how many L's you add, yeah. But it can be very expensive.
So what we still always discuss in the group is, do we really need to use spherical harmonics, or we can use the Payne way, which is what we use? Where is the advantage? Because we never find, at least for the type of network, which are probably very simple, so we just predict an energy and so on, or forces. So can you clarify?
Yeah, so I think it is task dependent, and also I think there's something that you point out. There's really kind of two issues here. There's expressivity. So from a mathematical perspective, like this is if you add higher L's, it's a more complete basis. So from that point, it's more expressive. But then there's an issue of like, at the end of the day, you have to train a model. It has to like play well with your optimizer. And so actually like teasing out what is a limitation due to like trainability. Like for example, before we've properly normalized the tensor product inside of E3N, like you couldn't train the models. So something as simple as the normalization might've been a bit wonky, could totally prevent an equivariant model from even being on par with an invariant model. There's a lot of moving parts. And I do think that's kind of a growing pain whenever you use a method that's just less battle worn, is that you don't necessarily have all those training tricks at hand. So when do you need to use higher L? I don't know. For me, generative models are a really good reason to, because you're basically expressing functions of 3D space, and that's much easier to do. It's much easier to express degeneracy with higher Ls. But I wouldn't always say like you should definitely go to higher L. I'm like, I don't know, you should do what works for you. But you should always know that you have those other operations to try and that those are available to you, but you don't have to use them.
Any more thoughts from the audience? And maybe Tess, we're both on that paper, but maybe you can elaborate more on sort of the role of what's it called? Scalars and handedness on generative models.
Yeah, I'm sure I have a backup slide here. I'm just not able to exit out of my, I'm glad you guys like that. Do I have it here? Okay. Okay. So I worked with Rafa and his awesome grad student Wuji and several other people on this. Really, I was more of, I think, just the equivariance doctor. You guys really did this one. And just, oh, I don't know how to make it not. Okay. Anyway, so this is a really cool paper. I highly recommend you read it. It's really fun. Basically about fine graining and using equivariant models to do this, to go from coarsened atoms back to these atoms. And one thing that was really cool is that whenever we coarsened down to 3 atoms and you wanted to produce a molecule, there was this issue of like, well, what side of this plane would you produce the different molecules? And it turns out that you needed what are called pseudoscalars in order to sort of define the handedness if you, in fact, were not inversion symmetric across this plane. And so it ended up being a very simple solution, but the reasons for it are really deeply rooted in representation theory. So maybe to specify a little bit, a pseudoscalar is like, this is a hand, but this is a right hand and this is a left hand. So there's still hands, but this is like 1 and this one's -1 of the same feature. So it's a scalar quantity. It doesn't change as you rotate, but it does change when you go from a left-handed to a right-handed coordinate system. And it turned out having just this additional special type of scalar and the interactions necessary to create them, that ended up being really helpful for generating some of these fine-grained structures. Is that what you were referring to?
Yes, like I think it was a perfect example of Gianni's question. So like
Okay, cool.
sign, right, that equivariance would have gotten us for free, yeah. And we didn't see until equivariance told us that we were missing pseudoscalar. So
yeah, pseudoscalars are really sneaky, but it's really mirror symmetry is really powerful. Like the inversion group is, even though it's only 2 elements, it's pretty powerful, especially with rotation. So yeah.
And I think we're good for now then. Thanks very much, Tess, for your talk. Thanks so much for the class.